All right, so now we'll move to the next part of the lesson, the section 2.2. So we are going to learn about Hooke's law and dynamics problem. Okay, so basically the difference between what you've done earlier. In the early exercise, we were dealing with problems that were in equilibrium, isn't it? So you had the string or the spring, it was in equilibrium, and then we just had to go with balancing forces, and we used the main equation we use here is tension equal lambda x over L. So this was what we did previously. Okay, so now in the next part of the lesson, what we actually do is we are going to consider the movement. We are going to consider the part where we actually release the object. Now, for example, over here, okay, so we'll go through this question. So basically, in short, what I want to say here is we are going to talk about, like, so basically you're going to pull the spring and you're going to release. The moment you release, what's going to happen? That's what we are going to talk about. So look, in exercise 2b, a particle of mass 4 kilogram is attached to one end P of a light elastic spring, PQ of natural length 0.5 meter and modulus of elasticity 40 Newton. Okay, the spring rests on a smooth horizontal plane with the end Q fixed. So it's really important that you read and immediately draw an accurate diagram. Okay, so what do we do here? They say the spring, now the elastic spring is PQ. This spring, it rests on a smooth horizontal plane with the end Q fixed. So the end Q is fixed. Okay, so this is the end Q. So with the end Q, so you can draw a spring here. So I think you can see the difference between a spring and a string. Okay, I'm drawing like this, or else you could even draw the line like this, but I'll draw the spring in this manner. Okay, so they say the natural length is 0.5, the lambda value is 40, the spring rests on a smooth horizontal plane with the end Q fixed. The particle is held at rest and then released. You see the difference now? We are not holding it and waiting, but now we release. Okay, so you can pull and release in a spring. You can pull and release, or basically in a spring, you can also what? In a spring, it's possible to compress, isn't it? You can. That's the difference between a spring and a string. In an elastic string, you can only pull the string, right? You cannot compress the string. Okay, the string will go slack when you try to reduce it. But the thing is, when it comes to a spring, it's possible to pull and it's also possible to push, isn't it? Both directions. Okay. That's the main difference between the spring and the string. Okay, they say here, find the initial acceleration of the particle if PQ is 0.8 meter initially. What do they mean by PQ is 0.8 meter initially? Okay, so what do you mean by PQ is 0.8 meter initial? So this is the particle P, right? The P, you're attaching the object. So they say this PQ length is 0.8 meters initially. So what does that tell you? We know that the natural length is how much? 0.5. So natural length is when it is, when the natural length is 0.5 meters. Okay, natural length is 0.5. The lambda value, they have told us the lambda value is 40 Newtons. All right, okay. So now you can see how much of an extension do we have here beyond the natural length. How much have we pulled? How much have we pulled it beyond its natural length? The total length 0.8, natural length 0.5. We have pulled it 0.3 meters beyond its natural length. Do you agree with me? We have pulled it 0.3 meters beyond its natural length. So this is the extension. Now, when you pull this, what do you create? Obviously, when you pull this, what do you create? You are creating a tension, isn't it? Now the object is initial, naturally over here in this length. So we have forcefully pulled it over to this point. And then definitely what builds up in the string, in the spring, you build tension, isn't it? It wants to go back to its original position. So then we are not going to apply any other, we are not going to draw any other force here because we are going to release it. So there's no other forces. So that means when you release it, it's going to accelerate and move towards. It's going to accelerate and move towards this side, move towards its natural length. Do you agree with me? It's going to accelerate and move towards its natural length. However, now you can see they use the word find the initial acceleration. Why do they say initial acceleration? Because the acceleration that this particle is going to experience, it's not going to be constant. It's not going to be constant because you can see the acceleration. You will learn more of this in simple harmonic motion, but over here, this acceleration depends on the extension. Do you see? So the more you pull, the more higher the acceleration. So then when it comes closer to the initial, when it comes closer to the natural length, the acceleration will drop. Not the velocity. Velocity will increase, but the acceleration will drop. It will move towards the velocity will increase, but the acceleration will drop since you're coming close and close to the natural length. So you will learn more about that later. At this point, all I wanted to know is that we don't have a constant acceleration. What they wanted to do is they wanted to find the initial acceleration. That means the moment you release, at that moment, what is the acceleration? So how do we find it? We will go with F equals ma. We will go with F equals ma. That's the way to find the acceleration, Newton's second law. So what is the force? The only force we have is the tension. Mass is 4 kilogram. Acceleration is what we are trying to find. So what is the tension? Always in elastic string or spring, tension is lambda x over L. Let's input the value. Lambda is 40. Extension. At this point, the extension is 0.3 over natural length 0.5 equals 4a. And now make acceleration the subject. Make A the subject. So acceleration is 6 meter per second square. This is the initial acceleration. Remember, this is not going to be a constant acceleration, but rather at this point, at this situation, this is the acceleration the moment you release. Okay, so let's try part B. All right, moving to part B. They say find the initial acceleration if PQ is 0.4. So if PQ is 0.4, I think you can see natural length itself is 0.5 meters. Natural length is 0.5. And they say PQ, this is P and this is Q. So they say PQ is 0.4 meter initially. So in this case, what have we done? If PQ is 0.4 meter, you need to realize that we have compressed, isn't it? We have compressed the spring. Okay, so in the previous case, we pulled the spring away from its natural length. Now we have compressed the spring inside. Okay, so when you're compressing it, now remember always when you're dealing with the spring, it wants to what? It wants to come back to its natural length. That's what it wants to do. It wants to come back to its natural length. So what happens here? In this case, you are creating not a tension, but you are creating a thrust because it will be pushing it where the spring will try to push its way to go back to its natural length. So this time you are creating not a tension, but you are creating a thrust. Are you with me? So this is the thrust. So now we are going to release it. So with this, we push it over here and we release. And then the object will start to move forward towards its natural length. So the pushing force, the only force acting here is the thrust. Okay, so there's no other force over here. So we'll apply F equal ma. The thrust, tension thrust, always for Hooke's law, it's lambda x over regardless tension or thrust. Okay, so mass is 4 kilogram into acceleration. So tension lambda extension. What about the extension in this case? The extension is the distance that you are moving from the natural length. How much did you vary from the natural length? So from the natural length 0.5, I've taken it to 0.4, which means I have compressed this by 0.1. I have compressed this by 0.1. So x is 0.1. Okay, the compression is 0.1. In this case, it's a compression. The compressed amount is 0.1 over natural length is 0.5 equals 4 into a. How much is the final answer? 40 into 0.1 over 0.5 into 4. You could type this whole thing in the cal. Acceleration is 2 meter per second square. Okay. Question number 2. A particle of mass 0.4 kilogram is fixed to one end A of a light elastic spring AB of natural length 0.8, modulus of velocity 20, and the other end B of the spring is attached to a fixed point. The particle hangs in equilibrium. Do you see this? The particle hangs in equilibrium, which means there's a couple of diagrams involved here. Okay, so there's a couple of diagrams involved. So in the first case, you have the particle. Now you have the spring, right? It's a spring. Now, when you have the spring with its own natural length, what are they doing? Now it's a light spring, which means the spring doesn't have its own weight. So when you attach a particle of mass 0.4 kilogram, definitely what's happening? Because of the due to the weight of the particle, okay, you realize the object will slightly displace, isn't it? So the natural length is 0.8. Natural length is 0.8 meters. Okay, and then due to the weight of the particle, okay, due to the weight of the particle, you can see it has displaced the spring a little bit below its natural length. Do you see? So I will say it is x1. This is the extension x1. This is the displacement. The amount has displaced under the particle's weight. All right, are you with me? So this is actually they say the particle hangs in equilibrium. They say it is then pulled vertically downwards through a distance 0.2 meter and released from rest. So while it's in equilibrium only, you're pulling it a further 0.2 meter down. You get it? So first what you need to do is, first we need to calculate this x1 distance, because from this particular distance of we are going to pull it further 0.2 meter down from this point. Are you with me? Okay, so first thing to do is to get this. What are all the forces acting here? Now at this point, this is in equilibrium. The particle hangs in equilibrium. So what are the forces acting here? You have the tension. Obviously, always a spring wants to go back to its original natural length. So you have the tension. I'll say T1. And what about, and it has its weight mg. Mass is 0.4 g. mg weight. And since this is in equilibrium, what do we say here? Definitely the tension must be equal to the weight. Do you agree with me? Tension must equal the weight. Okay, let's apply the tension equation. Is lambda x over L. So can I know what the lambda value? Lambda value was given. Modulus of elasticity, lambda value is 20. Extension is the length that we have taken the spring beyond its natural length. Beyond the natural length, I have taken this, the distance I have marked as x1. We do not know it. Over natural length is 0.8 equals 0.4 g. And now you can get your x1. So actually, you could maybe get your x1 in terms of g. Can I know how much this is? So let's see whether to get the answer in terms of g. It's better that you get, because you know when you use g as 9.8, you need to keep your answer to 2SF, 3SF, right? So we'll try to go with g until the end as much as possible. 0.4 into 0.8 over 20. Yeah, 0.016 or 2 over 125 with the g. Okay, so it's 2 over 125 g. Do you agree that this is the amount, the meter amount, that the particle, that the spring is displaced under the weight of the particle? Okay, so now after this point, what do we do? It is then the particle hangs in equilibrium. That's what I've done over here. It is then pulled vertically downwards through a distance 0.2 meter. Do you see what's happening? So from this, okay, so at this point, we again pull this. So we are pulling this particle from the equilibrium position, from its equilibrium position. So take all these distances, natural length. This was the equilibrium position. The red line I'm drawing in red was the previous equilibrium position. Are you with me? Okay. So now you are pulling this further. Now you have this x1 distance. And from the equilibrium position, you are pulling this a further 0.2 meter. Remember, diagram is key in these kinds of lessons. Natural length is 0.8. Do you see the diagram? It needs to be really understandable. Diagram is what helps you to understand what's going on here. Okay, so then they say that you're pulling it up further 0.2 meter and you're releasing. Now, the moment you pull it below its equilibrium position, what's going to happen? It will want to go back to its equilibrium position, isn't it? Because this is, when you pull it below its equilibrium position, the particle, it will want to go back towards its equilibrium position. So what do we create here? We create a tension here. Do you agree with me? So I'll say it as T2. The reason I marked the previous one as T1 is because there's another different tension that we are taking over here. So T2. Okay. And now again I have the, what do we have here? Tension. Then don't forget there is the weight. But this time, are these two forces in balance? Are they equal to each other? No, you have brought this 0.2 meter down from its equilibrium position. So which means if you pull it below its equilibrium position, this will again try to go, it will go definitely travel back up towards its equilibrium position. Are you with me? All right, so let's find the T2 value and then let's apply what they're asking us to find the initial acceleration, meaning the moment you release this will accelerate upwards because T2 and 0.4 G are not equal forces. T2 is definitely, the tension in the string is definitely higher than 0.4 G. Do you agree with me? This tension is definitely higher than the 0.4 G. Okay, the forces are balanced only in the equilibrium position. The moment you pull below the equilibrium position, this wants to go back up towards its equilibrium position. Okay. Shall we find the tension 2 value first? What is the T2 value? Tension is lambda x over L. What is the lambda value? Lambda is 20, right? Extension, can I know the extension? How do we define the extension? Extension is the length that you move beyond your natural length. So how much have you moved beyond the natural length at this point? What is the length that you have that the spring has displaced beyond its natural length? How much is it? Is it just the 0.2? No, it's 0.2 plus this x1. Both of them are contributing to the extension. Okay, so 0.2 plus the x1 value, which we found previously, divide by natural length is 0.8. Guys, do you agree? All right, let's, shall we just simplify 20 over 0.8 to make things easier because we got x1 in terms of G. So let's apply, what do we get here? 20 over 0.8, that is 25. 20 over 0.8 is 25 times 0.2 plus x1 is 2 over 100, 2g over 125. Do you agree? X1 is 2g over 125. Do you agree with me? So this is the tension. All right, now what do I need to apply? I have to simply apply F equals ma. We are supposed to find the initial acceleration. I know the object is moving upwards. So what's the upward force? Tension 2 is the upward force minus the weight is 0.4 g. Agreed? So this is the upward force is T2. So opposing that you have the minus 0.4 g. Agreed? Okay, equals to mass is 0.4 kilogram into acceleration is what we are trying to find. Okay, so we can now go for the G value. We use the G value as 9.8 and get the answer to 3SF or 2SF. You can type this whole thing in the cal. 25 into 0.2 plus 2 times 9.8 over 125 minus 0.4 into 9.8. Do you agree with me? I get 5. Perfectly, I get 5. 5 equals 0.48. So acceleration equals 5 over 0.4. 5 divided by 0.4 and I get 25 over 2, 12.5. It is coming perfectly to 3SF. So 12.5 meter per second square. This is the answer and this is the method that you need to get the answer. Okay, question number 3. A particle P of mass 2 kg is attached to the midpoint of a light elastic string of natural length 0.4 meter and modulus of elasticity 20 Newton. Okay. So lambda is 20 Newtons. Natural length is 0.4 meters. A and B, which are on the same horizontal level with AB 0.6 meters. The particle is held in the position shown. Okay, so in this question that they have shown, they are holding it with AP equal BP equal 0.5. So AP, BP, the distances are 0.5 meter each. And they are releasing this from rest. They are asking you to find the initial acceleration of the particle and state its direction. Okay. Okay, so they're asking you to find the initial acceleration and its direction. Okay, over here they have given you the initial diagram that you should start with. Okay, so then first thing is mark all the forces acting on this. Okay, what are all the forces we have? We have the weight. The first thing is we have the weight. Okay, how much is the weight? Particle of mass 2 kilograms. So weight is 2g. What else do we have? The particle is attached to this midpoint of the string, right? So what do you have here? You have the tension. In the string, you have tension. And when you consider these tension values, are you going to mark the same tension or different tension? You're going to mark the same tension because you can see this is a completely symmetric system. This is a completely symmetric system. So tensions must be the same. Agreed? The tensions must be the same because this is completely symmetric. Okay, the T values are equal. Okay. So all you have to do here is now, they have told you that they have pulled it over here. The distances are given to you. Do you see that these distances are given to you? So actually, when you look at the complete string now, natural length of this string was 0.4 meter. But I think you can see at this point, the whole string is 1 meter, 0.5 together, it's 1 meter, which means how much has this string stretched? What is the complete extension here? So from 0.4 meter to, it has gone to 1 meter. Do you see this? So which means the complete extension is 1 meter minus the 0.4 meter. 0.6 meters is the extension, this particular string. Okay. Okay, or else if that is tough, you could take this as two separate strings. Because the thing is, when you attach this, now they say the particle is attached to the midpoint, right? The particle is attached to the midpoint. So you could take this as two separate strings. When you attach to the midpoint, the natural length of each part of the string will become how much? 0.2 meters. So I could say the natural length of this, both of this is 0.2 meters. Okay, so this distance is 0.2. Are you all with me? So then how much is the extension? Each string has an extension of 0.3, 0.3. Agreed? Each string has an extension of 0.3, 0.3. Agreed? Okay, so now what we'll do here is I need to get this theta value. So you need to realize these theta values are equal. How do I get this theta value? Is it possible to get the theta value? I think you can see that this is 0.6 meters. So this is exactly in the midpoint, right? We've taken this particle from the midpoint. So this particular length should be 0.3 meters. Do you agree? So I think you can see it's easy for us to get the theta value. So I can go for, there's a right angle triangle here. So I could go for opposite over hypotenuse sine theta. Sine theta opposite over hypotenuse. So I think we can see the sine theta ratio is 3 over 5. Agreed? If sine theta is 3 over 5, cos theta ratio should be, if sine theta is 3 over 5, this is 0.3, this is 0.5 by Pythagoras theorem, this should be 0.4, right? Do you agree? You could apply Pythagoras theorem 0.5 square, or you could just draw a small triangle for the 3 to 5 ratio. Are you guys with me? You could just draw a small triangle for this one, sine theta, opposite over hypotenuse. If this is 3, if this is 5, the other side by Pythagoras theorem should be 4. So cos theta is adjacent over hypotenuse, 4 over 5. Agreed? Okay, so I have the cos theta value. Okay, I don't need this length over here. Okay, let's move on now. So what do we need to do here? Now we know we have to keep the particle over here and we are releasing it, right? The moment you release, what's happening? The particle will start to move up with an acceleration. Okay, so what we'll do here is now let's apply F equal MA vertically upwards. Okay, before applying F equal MA, shall we also find the tension? What's the tension here? Tension, tension in both parts of the string are equal. So tension, lambda x over L, lambda value, the modulus of velocity is 20, that doesn't change. The extension for one string is 0.3. Over natural length is 0.2. Okay, over natural length is 0.2. Okay, so then this is for one string. Okay, how much is the tension here? 30. So tension in each part of the string is 30. Okay, so now let's apply F equal MA upwards. So when you apply F equal MA upwards, what do you get here? T cos theta. You see that upwards you resolve T cos theta and again a T cos theta. So that is 2 times T cos theta. And you have to subtract it from the weight 2g. 2t cos theta, you subtract from the weight 2g equals mass into acceleration. Mass is 2 kilogram and acceleration is what you're trying to find. So 2 times tension is 30 times, cos theta is 4 over 5, minus 2 times g is 9.8 equals 2a. So you type everything in the cal and you should get your answer. 2 into 30 into 4 over 5 minus 2 into 9.8. This divide by 2 and we get the acceleration as 14.2 meter per second square. This was the answer, 142 over 5. So 28.4 equals 2a. Then acceleration is 14.2 meter per second square. So we get a perfect 3SF answer, isn't it? Right. We get. Okay, so then the next thing is you have to also give the, they want to say the direction. So you can see I used F equal MA upward. I got a positive answer, which means my acceleration is upward. So you can say initial acceleration is 14.2 meter per second square upwards. Okay. Question number 4. A particle of mass 2 kilogram is attached to one end P of a light elastic spring. The other end Q of the spring is attached to a fixed point O. The spring has natural length 1.5, the modulus of velocity 40. The particle is held at a point which is 1 meter vertically above O. Do you see what's going on here? So you are having the particle vertically above O. So O is the place where you are the fixed point, right? The other end Q of the spring is attached to a fixed point O. So the particle is held at a point which is 1 meter vertically above O. Okay, I think you can see natural length is also 1.5. So if the particle is 1 meter vertically above O, you need to realize the spring is kind of compressed, isn't it? And released from rest. Find the initial acceleration of the particle stating its magnitude and direction. Okay. So if you draw the diagram, it's going to be look like this, right? So it looks like this. The particle is over here. Natural length is how much? Natural length was 1.5 meter. So natural length 1.5 meter is a little bit higher than what we have, right? So let's say this is the natural length. So this is the point O and this is the point P. So they say the particle is 1 meter vertically above O. So this is 1 meter. Okay, so this is 1 meter. Now the thing over here is, okay, so there's a vertically above O and the particle is released from that. Find the initial acceleration of the particle stating its magnitude and direction. Okay, so over here, what are the forces that we need to consider? Okay, so I think over here now, normally, when you have a weight on top of the spring, okay, what do we expect? We expect there to be, due to the weight, there has to be some sort of a compression inside, isn't it? Okay, so there has to be some sort of a compression inside. So we really don't need to find that compression. You could find it. but it's actually not required over here. So they have given you this length. Okay, so let's just go for an assumption. What do we have here? Let's say that the particle, basically this 1 meter, the problem here that you need to think is whether this 1 meter distance, is it below the equilibrium position or is it above the equilibrium position? What do I mean by equilibrium position? Now, when the particle is, when the spring has the weight, okay, when the spring, when you attach the weight of this, when you attach this weight on top of the spring, the natural length will anyway, the natural length anyway, you will find there is a compression. So then from that point, they have moved this to this point where it is 1 meter away from O. So at this point, I do not know whether the the equilibrium position is below or is it above. Okay, so actually you don't need to find it. Okay, you don't need to find it. You can just go with this. Okay, let's just mark with what we have. If our answer is wrong, okay, the thing is this. If our answer is wrong, I will get a negative answer. That's what I'm going to get. I will just get a negative answer. Okay, because the thing is my assumptions of my directions are going to be wrong. Okay, so if the equilibrium position is like below the 1 meter, that means you have pulled this object upwards. Are you guys with me? Let's say for a moment, if the equilibrium position, that means with the only with the weight, let's say the with only with the weight of this particle, if this in equilibrium, if this was over here, it means you have pulled it upwards, which means when you are releasing it, it will start to move down. Or if the equilibrium position is actually over here and you have pushed it further down to reach this 1 meter, it means when you release, it might go up. Okay, so that is the issue you have over here. The problem is where is the equilibrium position? Is it up or is it down? Okay, so if it is up, then when you have pushed it down with the to make it 1 meter, and when you release, it will move towards the equilibrium position upward. If the equilibrium position with the weight is down over here, it means you have pulled it up, and when you release, this will start moving down. That is the problem that we have over here. Anyway, so what I'll assume is we can go with an assumption. Okay, and if it is wrong, you will get negative answer. That's all. So let me assume that this is up over here. Okay, so in that case, I'm going to assume that this is going to have a tension, right? Because in that case, it will start, if the equilibrium position is on top, it will start moving upwards. Upward acceleration. So what else do we have other than the tension? I'm assuming that the equilibrium position with the weight is somewhere like over here. Okay, definitely it has to be below the natural length, isn't it? Definitely below. So I'm assuming it's somewhere over here. So for the particle, when you over here, when you release it, it wants to go back to its equilibrium position. That's how it is. There are two ways to do this. Either the equilibrium position is here or here, down, even below the 1 meter. Okay, you could actually find it, but anyway, we can go with this. We don't need to go there. Okay, so this is the tension. What else do we have? We also have the what of the object. We have the weight of the object, right? So the mass is 2g. So weight is 2g. Shall we find the tension? It's possible for us to find the tension here, right? Lambda x over. So what is the tension? Lambda value is, the modulus of velocity is 40. Extension. You do realize it's possible for me to find the extension here without any issue, right? So that's why I can directly go with this. Okay, it's possible to find the extension. What is the extension? So below the natural length, the particle is now 0.5 meters below its natural length. Do you see? So then extension is 0.5 over natural length is 1.5. Guys, do you agree? Can I have the answer here? 40 into 0.5 over 1.5. How much is it? 40 into 0.5 over 1.5 is 40, 40 over 3. Take the exact figure. 40 over 3 Newton. Okay, so now let's go for F equal ma. I'm assuming that the equilibrium position is upwards, which means I'm assuming this is moving up. So now when we apply F equal ma upwards, when I apply F equal ma upwards, what do I get here? Tension upwards opposing 2g equals mass. Mass is 2 kilogram into acceleration is what I'm trying to find. So tension is 40 over 3 minus 2 into g is 9.8 equal 2 times a. How much is it? 40 over 3 minus 2 into 9.8. That's minus 6 points. So actually, that's a recurring figure, right? Okay, don't take that. Minus 94 over 15 here, divide by 2. Okay, so divide by 2. And you get minus 47 over 50. Now, are we going to keep this answer as an exact figure? Minus 47 over 50? No, you can see that I have involved G equal 9.8 here. So definitely leave your answer to 3SF. So minus 3.133. Why am I getting a negative figure for the acceleration? Because, see this children, this is what I'm trying to say you. What I assumed here that my equilibrium position is above the 1 meter is actually wrong. So I assume this is going up. But what's happening? This is actually moving downwards. Why? That's why you are getting a negative figure, which means the true equilibrium position is actually below, is even below the 1 meter. That means with the weight, with the 2 kilogram weight, the spring is over here with the 2 kilogram weight. And then you have basically pulled it up. You have pulled this up, and when you release, it will start to move down. You get it? That's what's happening here. So then that's why they ask you for the magnitude and direction. So you can say the magnitude means the value without the sign. Don't give the sign. What is the sign? Calculate the stating its magnitude. What's the magnitude of acceleration? Write down. Magnitude of initial acceleration is how much? The magnitude of the initial acceleration is 3.13 meter per second square. Agreed? And what's the direction? Direction is downward. Okay, you guys can understand why we don't need to find the equilibrium position specifically, right? Because I already know all the distances. I don't need to find the equilibrium position. Okay. So over here, the negative answer means the equilibrium position is below. So therefore, the particle will move down towards to move towards the equilibrium position. Okay. Question number 5. A particle of mass 1 kilogram is attached to one end of a light elastic spring of natural length 1.6 meter and modulus of velocity 21.5. Let me write down all the information. Natural length is 1.6 meter. Lambda is 21.5. The other end of the spring is attached to a fixed point O on a rough plane, which is inclined to the horizontal at an angle alpha, where tan alpha is 5 over 12. The coefficient of friction, okay, they have given us tan alpha. I think the moment you see tan alpha is 5 over 12, we actually draw the triangle, right? We can draw the triangle and get what? Cos alpha and sin alpha. Tan alpha opposite over adjacent, 5 over 12. How much is the hypotenuse according to Pythagoras theorem? 5 square plus 12 square square root 13. So which means sin alpha ratio is gonna be 5 opposite over hypotenuse 5 over 13. Cos alpha ratio is gonna be 12 over 13. So I have all of that. And then they say the other end of the spring is attached to a fixed point O on a rough plane, which is inclined to the horizontal at an angle alpha. The coefficient of friction is the mu value. The mu value is given to you as half. The particle is held at rest on the plane at a point which is 1.2 meter from O down a line of greater slope of the plane. Do you see? How do we have the particle? The particle is held at rest on the plane at distance 1.2 meter. Then you can see natural length itself is 1.6. So if you're holding it at 1.2, it means you're compressing the spring, right? From O down a line. So it's down along the, okay, so let's draw this. Okay, so this is the angle alpha. And you have your particle, the point O. So this is the particle. Okay. So the particle is held at rest on the plane at a point which is 1.2 meter from O. So this is 1.2 meters from O. While you can clearly see natural length itself is 1.6, which means this is compressed, which means the spring is compressed. Okay. And then what do they say here? Natural, let me mark the natural length as well. Natural length is 1.6 meter. So natural length is the 1.6 meter. Okay. Now what do we do? Okay, they say the particle is okay. The particle is released from rest and moves down the slope. Find its initial acceleration. So it's moving down the slope. You're supposed to find the initial acceleration. So it's going to go in this direction, and they're asking you to find the initial acceleration. Okay, so how do I get the initial acceleration? The first thing to do here is to mark all the forces. Shall we mark all the forces? So what are the forces? First thing is you do realize the spring is compressed. The spring is, oh yeah, obvious ones are weight, right? So we'll mark, anyway, let me mark the tension thrust first. So what do we have here, tension or thrust? Since the spring is compressed, you will have a thrust, which means it will be pushing. So you will have a thrust in this direction. There'll be a thrust here. What else do we got here? This is a rough plane. All right, so it's a rough plane. What else do we have? Always we mark the weight. What's the weight? Mass 1 kilogram. So weight is weight 1g. And what else? Always you have the normal reaction, right? Perpendicular to the surface, you have the normal reaction. And they say this object is moving down, right? So if it is moving down, your friction will be acting the opposite direction. So friction will be upwards. I have this T here. So upwards, opposing, I have the friction, and it is, since the object is moving, it will be the maximum friction, right? The object is moving on the rough plane, so you will not have just the normal friction, but you'll have the maximum friction. So all right, so we have everything here. All we need to do is to calculate the tension, the thrust over here, and we can apply F equals ma. Okay, we just need to go with F equal ma. All I have to do is to find this unknown acceleration. Okay, so let's get tension equals lambda x over L. Lambda value is 21.5. What is the extension? Actually, in this case, it's the compression. Natural length 1.6 to 1.2. How much have we compressed? 1.6 minus 1.2. How much is the compression? 0.4. Over natural length is 1.6. How much is the tension? 43 over 8. 43 over 8 newtons. And now we can go for, before going for F equal ma, let's resolve. I think we need to resolve the weight component here, right? Because you can see now when we are on these kinds of planes, we use the x-axis along the plane and the y-axis perpendicular to the plane. So you can see here this 1g. So this is basically m1. You have to resolve this 1g, right, into directions that actually agree. So you remember how this works. The alpha comes here. So what is the component? This is the perpendicular component is 1g cos alpha. The other one to the other side, this is 1g sin alpha. Guys, do you agree? So when you take equilibrium along this to this side, equilibrium perpendicular to the plane, you do realize the object is moving along the plane. Forces that are perpendicular to the plane must be in equilibrium, isn't it? When you are moving parallel to the plane, the perpendicular to the plane direction forces are equal to each other, isn't it? So when you consider equilibrium perpendicular to the plane, what do you have here? Perpendicular to the plane, normal reaction is equal to 1g cos alpha. Guys, do you agree? Normal reaction is equal to g cos alpha. What is cos alpha? 12 over 13. So 12g over 13. Can you see? Cos alpha is 12 over 13. So 12g over 13. Okay, so why do I need the normal reaction? Because I need the normal reaction to find the F max, maximum friction. So what is the maximum friction? It's always equal to mu r. Mu value is half. Normal reaction is 12g over 13. How much is it when you simplify? Half into 12 over 13 is 6g over 13. Half into 12 is 6g over 13, right? I didn't give the g value in the cal yet. I didn't use g as 9.8 just yet. Okay, so we are ready with everything. So I know the tension now. I know the friction. So everything is ready. All we have to do is apply F equal ma downwards, right? We know the object is moving downwards since it's compressed. So what are the downward forces that is assisting the motion? You have the weight component. Is that all? Is that the only force that is assisting in this direction? No, you can also see the thrust in the spring. The spring is compressed, so this thrust is also pushing it downwards, right? So G sine alpha plus the thrust is opposed by the maximum friction. Agreed? Those are the forces that we have. So this is equal to mass 1 kilogram into acceleration. G, what is sine alpha? Sine alpha is 5 over 13. Plus tension is 43 over 8. F max 6g over 13 equals A. Let's give G as 9.8 and get the answer. So 9.8 into 5 over 13 plus 43 over 8 minus 6 into 9.8 over 13. And you get this answer, so definitely give it to 3SF. You know, when you have G with 9.8, you give the answer to 3SF, 4.62 meter per second square. Meter per second square, this is the answer correct to 3SF. Moving on to part B, they say without doing any further calculation, state how your answer to part A would change if the coefficient of friction between the particle and the plane was greater than half. So they are not asking you, it's just 1 mark. You have to give a kind of like a description what would happen if the mu is greater than half. So let's go into the calculation. Let's go into the calculation. If mu is bigger than half, what would change? Is the tension going to change? If mu is greater than half, is the tension depending on mu? No. The tension value stays the same. Normal reaction, is it going to change? G cos alpha? No. What is going to change? F max mu r, if mu is bigger than half, I think you need to realize your friction will what? Increase or decrease? If your mu is bigger than half, if greater than half, this value overall would increase or decrease? It will increase, right? The friction value would increase. So if the friction value increases, I think you can see in this equation, everybody else says G sine alpha downward force, tension, we just found it doesn't change. The F max will increase, right? So which means you're subtracting by a larger value, which results in what? Which results in this value becoming lower. So then so which results in the whole value becoming lower. So when the whole value is lower, your acceleration will decrease. Okay, so just give that as an explanation. So you can say the friction when mu increases. When mu increases, what happens? Friction will increase, right? Friction increases. When mu increases, friction increases. So that happens. T plus the G sine alpha or G sine alpha plus T minus F max equals MA. What happens? So what happens to this person? This will decrease, right? Okay, do you get what I'm saying? So when the F max increases, the overall value here will decrease. Okay, so the resultant force down the plane will decrease. Resultant force down the plane decreases, which results in what? Therefore, acceleration A will decrease. Acceleration will decrease. Okay, because when the friction increases, its value as a whole will decrease because F max is a negative. This value as a whole will decrease. Or you can just, you don't need to write this, but at least you have to write this. Resultant force down the plane decreases.